Hi sir, my name is K. Kumar. Roll number is 2295503117 from Mechanical Department. My topic is modes and mechanisms of heat transfer. Introduction to heat transfer. Heat transfer is a process of energy moving from a warmer object to a cooler one. There are three main modes of heat transfer: conduction, convection, and radiation. Understanding these modes is crucial in various engineering and natural phenomena. Conduction, heat transfer, conduction, heat transfer. Conduction is the transfer of heat through a material without any movement of material itself. This mode of heat transfer occurs in solids where molecules transfer energy from collisions. Material with higher thermal conductivity heat transfer more efficiency through conduction. Convection, heat transfer. Convection involves the transfer of heat through the movement of fluids, either liquid or gases. There are two types of convections: natural convection due to the density of differences, and forced convection due to the external force. Convection is an essential mechanism in heating the cooling system. Radiation, heat transfer. Radiation is the transfer of heat through electromagnetic waves without the need of a medium. All objects emit radiation with the amount of depending on their temperature and emissivity. Radiation can transfer heat through a vacuum, making it crucial in space application. Thermal conductivity. Thermal conductivity is a material property that determines how well it conducts heat. Material with high thermal conductivity transfer heat more efficiently. Insulators have low thermal conductivity, reducing heat transfer through them. Heat transfer coefficients. Heat transfer coefficients quantity the rate of heat transfer between a surface a fluid. They are influenced by factors like sur- surface roughness, fluid properties, and flow conduction. Understanding heat transfer coefficients is vital in designing efficiency heat exchangers. Flournoy's law of conduction. Flournoy's law heat states that the rate of the heat transfer through a material is proportional to the temperature gradient. The thermal conductivity of the material determines how much heat is transferred. This law is fundamental in analyzing conduction heat transfer in solids. Newton's law of cooling. Newton's law describes the rate of heat transfer between a surface and a fluid. It states that the heat transfer rate of proportional to the temperature differences between the surface and the fluid. This law is crucial in analyzing convective heat transfer in various applications. Stephen Boltzmann law. The Stephen Boltzmann law relates the total energy radiated by an object to its temperature. It states that the radiative heat transfer rate is proportional to the fourth power of the absolute temperature. This law plays a significant role in understanding radiation heat transfer. Application of heat transfer. Heat transfer principles are essential in various engineering fluids like thermodynamics, HVAC systems, and heat exchangers. Understanding heat transfer mechanisms is crucial in optimizing energy efficiency and system performance. Natural processes like weather pattern and climate change also involve heat transfer mechanisms. Heat transfer exhaustive techniques. Engineering use various techniques to enhance heat transfer rates, such as increasing surface area, using fins, and adding turbulators. Heat transfer excitement the crucial in improving system efficiency and reducing energy consumption. These techniques are applied to in heat exchangers, cooling system, and thermal management applications. Challenges in heat transfer analysis. Analyzing heat transfer in complex system with multiple modes of heat transfer can be challenging. Factors like consistent heat transfer, phase change, and non-uniform properties complicated heat transfer analysis. Advanced computational tools like computational fluids dynamics (CFD) are used to model and analyze heat transfer in such systems. Future trends in heat transfer. Future research in heat transfer focuses on nanoscale heat transfer, thermal management of electronics, and renewable energy system. Advances in material science and nanotechnology and enabling the development of novel heat transfer solutions. Sustainable heat transfer technologies are being explored to address environmental concerns and energy efficiency. So, conclusion: heat transfer is a fundamental forces the nature and engineering influences various systems and phenomena. Understanding the modes of technique mechanisms of heat transfer is crucial in optimizing energy efficiency and system performance. Continued research and innovation in heat transfer will drive advancements in technology and sustainability. So here Q is equals to h mu by T, where Q is the local flux density, H is the heat transfer coefficient, delta T is the temperature difference, where Q is equals to minus K T, where Q is the local heat flux density, K is the material conductivity, T is the temperature gradient. Radiation Q is equals to E epsilon naught T power 4, where Q is the power of the radiation from object. Nu is the Stephen Boltzmann constant. Epsilon naught is the emissivity of the surface of the material. So thanking you, sir.